All right, welcome back to another video of 1MO3. And now we're going to be talking about the bond type of a crystal and how they differ from one material and another. So if you want more detail, do check it out in the textbook chapter 2.6. Okay, so in your high school chemistry class, you may have learned that there are four fundamental type of bonds. There's ionic, covalent, metallic, and secondary bonds such as hydrogen and van der Waals. And so in the previous video, you have seen how ionic bonds interact with each other. And so these bonds are differ from ionic bonds, but they all have a similar type of behavior of attraction and repulsion balancing each other out. And so ionic bond are one of the strongest bonds out there because of how strong the ion are bonded together. And in general, ceramics material have ionic bonds. And that's the reason why ceramics tend to be very tough, very strong, with high stiffness. Covalent bonds are often found in polymer. It is a very strong bond, and one thing that is rather puzzling for the newcomer into material science to think about is why polymer are relatively weak. That actually depends on how you look at polymers. Some polymer is actually very strong. For example, we can think of a system that have purely covalent bonds, such as carbon fiber or carbon nanotubes. These kind of structures are full of covalent bonds, and they are a single strand of fiber with very strong bonds together. Another example is high-density polyethylene. It's a polymer fiber, and it has incredibly strong bonds together and with very strong strength. However, some polymer have very low strength. So why is that the case? That comes to other bond. Metallic bond is a relatively strong bond as well. The way it works is that in the metals, the electron can be activated by thermal energy. By doing that, they go from the valence band to the covalence band. And these electrons are acting like a sea where it can hop from one atom to another atom. And by doing that, this whole system are sharing those electrons of sea of valence electrons. And by doing that, we have basically bonded all those atoms together. And metal use this type of bonds. And the interesting things about this particular type of bonds is that metal easier to deform into the shape you want, because when you arrange the atom, it will basically have a new formation. Whereas ionic bond, a little bit harder to do that. And so ceramics tend to be more brittle compared to metal. Whereas metal, you can deform it into shape you want. So for example, forging is one example of why we have used metal in many applications on both structure as well as in the old days we use it for weaponry, because we can form it into a shape that we want. The reason why polymer is one of the weaker material compared to metal and ceramics is because polymer not only consists of covalent bonds, but it also consists of secondary bonds such as hydrogen and van der Waals. So earlier we talked about if you have a single strand of polymer, they might be very strong. However, polymer are usually consist of both covalent bonds, so these are the long chain of carbon-carbon bonds. But then in between one of these strands, they are bonded together by hydrogen or van der Waals, which are much weaker bonds compared to the previous three. And so you can think of an analogy where polymer are kind of like spaghetti where it wrapped together. The spaghetti is much relatively strong, but the the interaction between the long chain, which is between the spaghetti, can be relatively weak. And so when you press spaghetti together, they can deform quite easily, not because you're actually breaking this spaghetti, but rather the spaghetti are sliding from each other. So these long chain can slide from each other, just like how a spaghetti would work. Okay. And so these are the class of material that are available. Like I said, the ceramics tends to have both ionic or covalent bonds. Metal tend to have a metallic bond. And this is one of the reasons why metal are an electrical conductor. We'll talk about that in later lecture. But metal are electrical conductor because the electron went to this covalent bands. And so the electrons act like a sea and it can hop from one place to another. And if the electron can flow, that's basically current, making them electrical conductive. Ceramics are usually not a conductor. Okay, organic matters are another class of materials. It included natural material, polymer, as well as elastomer, and that involve both covalent bonds as well as the secondary bonds, which are hydrogen and van der Waals force. And then finally, we have a hybrid materials. We have the class of hybrid material, which is basically mixing all the previous class of material together. And this actually tend to come up with the best of both worlds sometimes. And so you can mix polymer that are relatively weak with ceramics fiber that are relatively strong but brittle. By putting them together, you make sure you can ensure that they're both strong and tough at the same time. So previously, we talked about how bond strength can have an effect of melting point. And since ionic, covalent bond, and metallic bonds are relatively strong, in general, metal and ceramics tend to have a much higher melting point. And ceramics tend to have the strongest melting point, highest melting point, because the bond strength is stronger than metallic bond as well. There is exception, and the exception is the leeway to the next topic, which is atomic structure and crystal structure. So right now we're only looking at the bonds, but we're looking at only 2 atoms. What happens if you have more atoms together, which they create as some kind of structures? Then now we need to think about how many neighboring atoms are interacting with each other, and that leads to those kind of exceptions. But in general, ceramics tend to have very high melting point. Metals tend to have intermediate melting point. And then lastly, polymer, such as thermoplastic type of polymer, have the lowest melting point. And the reason for that is because polymer consists of covalent bonds as well as the secondary bond. And the secondary bond is the weakest. And so to melt polymer, you don't actually need to melt the covalent. You don't need to actually break the covalent bonds. All you need to do is just break the secondary bond. And so polymer tend to have the lowest melting point. And why is that important? Well, that leads to a whole bunch of different type of application. So if you think about that, polymer have very low melting point. So it's very good to make it into shape. And that's why a lot of 3D printer are using polymer filament. And they have very low melting point, and you can make anything in a relatively low cost. And that's why polymer is being used pretty much everywhere. Ceramics have extremely high melting point, and so it's very good as a thermal insulator, where you want to make sure that the structure do not break at a particular, to withstand a particular temperature. So you can imagine space application. If you're a spaceship re-entering onto the Earth, the outer shell we normally would put ceramics tiles on top of that as a thermal insulator, because that they can withstand the high temperature without melting. Metal have this intermediate melting point, and therefore you tend to use them to forge into the structure that you want. And after that, because metal have this unique material property where it can be relatively ductile, when you compress or reshape it at high temperature, it can turn into any shape you want. And so it's tough. It's an intermediate melting point, and that's why they're being used in many other structural applications. So that's it in terms of the bond types as well as different type of materials. If you want more details, please go check out chapter 2.6. In the next video, we'll start to talk about crystal structures.